So once again, welcome to a new problem. This time we have a tennis racket. We have a tennis racket, and then there's a nylon string that just runs across the racket like that, and there's a force of 275 newtons being applied on the racket, um, and also the string itself has a span or length. This is a nylon string, has a length of uh, 30 centimeters. We can change that to meters right away by dividing by um, doing a conversion, unit conversion, 1 meter per 100 centimeters, and that gives us 0.3 meters. Also, the we're given that the nylon itself from a cross section. So if you look at the nylon from this side, for example, you see a cross section with a diameter of 1 millimeter, and that's pretty small, but we can change that to meters by multiplying 1 centimeter is in 10 millimeters and then shifting that to 1 meter in 100 centimeters, and that's going to give us 0.001 meters. So that's the cross section uh, of the nylon. In this problem, we want to find uh, the the change in length when the force is applied. So what we're saying is that the initial length is 0.3 meters, and then when the force is applied, it stretches. So there's a force being applied right there, and then the whole string stretches, and we want to find out if this happened to be the initial length, and this is the final length, then we're interested in finding the change in length, which is the difference between the final length and the initial length. So it's being stretched. Um, the main concept that we're going to use is Young modulus of elasticity. Okay, Young modulus of elasticity. I was going to say elasticity, but it's elasticity. So this is Young modulus of elasticity, and it so happens that E is the same as stress over strain. And the reason why we're going this route is because we do have information, or we can get information about the elasticity of the nylon, E. And also remember that stress is force over area, and that's the cross-sectional area. We have to get that from this diameter using pi r squared. So we can use pi r squared to get that. And then stress over strain is force over area divided by strain, which is the change in length over the initial length. And you can see if we reorganize the problem, we end up having E times delta L over I becomes equals to the force over the area, and that way we can always find that the delta L change in length is the same as the force times the the initial length over the modulus of elasticity times the area. And pretty much what happened in this case is that we did have to multiply both sides by the reciprocal of E over delta L, like that. And so we have a new arrangement that can help us solve for the change in length. So, going to the next slide, we still apply the same formula. Delta L equals to the force times the original length over the modulus of elasticity times the cross-sectional area. So the force was given as 275 newtons. The original length, as you can recall, was 0.3 meters, and then the modulus of elasticity happened to be 500 times 10 to the 6 Newton per meter squared, almost similar to pressure. When you think about pressure, okay, and then we want to multiply that by this area. That's the cross-sectional area, pi r squared. So this is going to be pi times the radius. Remember, the radius is half the diameter, so this is the diameter itself. So to get the radius, we have to divide that value by 2. So we end up having 0.001 meter divided by 2, and then you square the result. So pi r squared. Okay, that's the radius itself, pi r squared. When we plug in the numbers, we end up getting approximately 0.21 meters as the stretching length, as the stretching length. So hope you enjoyed the problem. Once again, we had a force that was applied to the nylon, and it happened to stretch the nylon, as you can see right there. This was the original length, and then when it gets stretched, there's a change in length, which is what we're looking for. That value is hidden in the strain itself, and strain is defined as a change in length over the original length. But since we're given the force and the diameter, we can always get the cross-sectional area. So that means we have 3 different units that we're given. So we have the force, we have the area, and we have the original length, and we also have Young's modulus of elasticity. We reorganize the problem to solve for the change in length delta L, and as you can see in the next page, we plug in the numbers just to recall that the radius is half the diameter. So this radius right here is half the diameter, and then we end up getting the change in length of 0.21 meters. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.